Look at any engines, it looks strong and right, but without dynamics. It's just called metal. Dynamics is what breathes life into the machines. It controls the movement, the balance, and the speed. Today, we are going to see exactly how it works. Let's get started. So, what is an electric motor? Simply put, it's a device that takes electrical energies and turns it into mechanical motions. And there are main types you need to know. First, DC motors, perfect for small fans and pumps. Second, AC motors, used in huge industrial machines. Third, servo motor, for precise control like robotic. And finally, stepper motor used in positioning system like CNC. Now let's dive into our main focus, DC motor. Let's look at the fundamentals. First, how it works. It simply converts direct current into mechanical motions using electromagnetic principles. Okay, why do we use it? Because it has a simple structures and easy speed control suitable for control system. Third, we can find DC motors in everything, especially in vehicles, pumps, and robotics. And we have the types of DC motors: brush DC motor, brushless DC motor, series DC motors, and shunt DC motor. Look inside the machines. The main part of DC motors, we have the stator. It creates the magnetic fields. The rotor, this is the rotating part that carries the current. The commutator, it cleverly reverses the current direction to keep the motor rotating. The brush, they maintain electrical contact with the rotors. Shaft, which is the mechanical backbone that transfers the motions. And finally, the power supply, which provides the DC voltage to drive the whole motors. So how does it all come together? It starts when a DC current flows through the coils. Immediately, this creates a magnetic field around it. The field interacts with stators. As a result, a magnetic force is produced, causing the rotor starts rotating. But to keep it moving, the commutator plays a key role here by reversing the current directions, and this is exactly why the rotations continue smoothly in the same direction. It's a perfect loop to physics in action. Let's tie everything back to our main topic, DC motor dynamics. When we talk about dynamics, we are looking at how the motor actually behaves under different conditions, like changing load and time. To understand this, we focus on 3 key parameters: speed, torque, and response. DC motor torque analysis. Why is torque important? To provide rotational force, determining load capability, essential for performance. Torque equation: T equal KT phi IA. T is a torque, KT is a torque constant, phi is a magnetic flux, and IA is armature's current. Torque is directly proportional to flux and armature's current. How to use in selection: increases load, higher torque; increases armature's current, increases flux, take starting torque. We have a key point here. Higher torque allows the motor to handle heavier loads, ensure smooth operations, and improve system performance. DC motor speed analysis. Why speed is important? Determines system performance. Most match application requirement, affect efficiency and stability. Speed equation: N proportionals with V minus IA RA over phi. N is the speed, V is supply voltage, IA is armature's current, RA is armature resistance, phi is a magnetic flux. How to use in selection? Increases voltage mean higher voltage, higher speed. Increases load, higher load, lower speed, and higher IA. Adjust flex, change flex, control speed. DC motor response analysis. What is motor response? Motor response is how quickly the speed or current change with condition change. Important for control, stability, and accuracy. Fast and stable response improve system performance. Dynamic equation: GW dW over dt plus dW equation Tm minus TL. Factors affecting response: inertia, frictions, motor torque, load torque. How to improve response: reduce inertia, reduce frictions, increase motor torque, and use a control system. Okay, we have typical time response, and we have the vertical line is a speed and the horizontal line is a time. Right time to reach 90% of final value. Settling time to stay with plus minus 5% of final value. Overshoot, maximum peak above final value. Good response means short rise time, small overshoot, short settling time, high stability. Okay, we have four main applications in DC motors. We have those in everyday. At first, we have electrical vehicles, conveyor belts, fans and pumps, and robotic. The conclusion, choosing the right motor is key to a successful mechatronic system. Speed plus torque plus response, because any right motor equals better performance, efficient, reliable, well matched. In the end, we can see that any successful project starts with good math and calculations. Theory and dynamic help us understand the machine before we build it. This is how we avoid mistakes and make our design safe and strong. Thank you for watching, and I hope you enjoy in this video.